Algebra 1, Investigation 1, is all about probability of an event, and we're really just looking at simple probability here. There is an experiment within here that I will allow you. You can do that wherever you are. There's lots of ways to do it. I will just make up some data so that I can show what the probabilities would kind of look like. But simple probabilities, just some beginning questions here to kind of get our minds back into probability. Number one, what's the probability of rolling a 3 on a number cube? Remember that whenever we talk about probability, especially theoretical probability, what we are saying is the in our proportion here, in our ratio, we are talking about the number of successes versus the total number of possibilities. So in this case, on a regular number cube, we have 6 total sides, so 6 total possibilities, and only one of them is a 3. So we only have one that is successful when we want to get that 3 on a number cube. So we'd say the probability of getting a 3 is 1/6. Number 2 says, if a jar has 4 blue, 3 green, and 3 yellow marbles, what's the probability of choosing 2 yellow marbles without replacement? Well, when we look at this, what we're really trying to find is the probability of 1 yellow, and then again the probability of another yellow. These, whenever we find this, it's going to be dependent probability, we're going to multiply them together. The probability of getting the first yellow marble, well, there are 10 marbles in the jar and only 3 of them are yellow. So the first probability is 3/10. And it might be pretty tempting to say, well, then the other probability would be 3/10. But this keyword of without replacement means if I pick a yellow, I'm not returning it to the jar. So I actually only have 9 marbles left. And since I picked out a yellow, 2 of them are yellow now. So I would use this to then simplify a bunch of different things and figure out that the probability of getting 2 yellows without replacement is 1/15. How about this? If you flipped a coin 10 times and each time it came up heads, what's the probability that the next flip will be heads? Well, once again, it might be tempting to say, well, the probability of getting those 10 times getting heads is a half times a half times a half times a half all the way through. That's not what it's asking at, actually. It says, what is the probability that the next flip will be heads? Well, we have to throw out everything we know up until that point. We don't care that it came up heads 10 times before that. What we want is just the typical theoretical probability. There are 2 sides on the coin, one of them is heads. So what's the probability that the next flip will be heads? It's still 1/2. Doesn't matter if we get 100 times of heads coming up, then the next probability will still be heads. Okay, so diving into this investigation, probability is the measure of how likely a given event or outcome will occur. The probability of an event can be written as a fraction or decimal ranging from 0 to 1, or as a percent from 0% to 100%. And you can see this range with different words to describe the different parts of this. So in the math language, we have 2 different vocab terms. An outcome is a possible result of a probability experiment. Like with our number cubes, our outcomes were 1, 2, 3, 4, 5, and 6. And an event is an outcome or set of outcomes in a probability experiment. So an event happening, like getting a 3 on that number cube, is an event in that experiment. So let's describe each of the events below as impossible. Okay, that's 0%. Unlikely is kind of between 0 and 50. As likely as not, meaning we have a 50-50 chance of getting it. Likely is in between, and then certain is 100%. So Jake rolls a number less than 7 on a number cube. Well, if I think about a number cube, all of the numbers are less than 7. So this would be certain. February will have 30 days. Well, if you think about the calendar and think about February, February only has either 28 or 29 days. So February will never have 30 days. This is impossible. Number 3, a coin tossed will land on tails. Well, like we looked at before, tails is half, 1/2, 1 out of 2, or 50%, which means it's as likely as not. And lastly, Shayla correctly guesses a number between 1 and 100. Well, the probability that she will get that one number is pretty small. It's not impossible though, it's not 0%, but we would say it's unlikely. Okay. So experimental probability is different from the theoretical probability that we saw in our warm-up questions. Experimental is the measure of how likely a given event will occur based on repeated trials. So like I showed before, we have this ratio, but this time we are saying the number of times the event actually occurred in our experiments versus our number of trials. For example, if I flipped a coin 10 times and it came up heads 4 of those times, my experimental probability reduced is 2/5. So this is the experiment that I was mentioning before, and you can do this with marbles or colored squares or whatever you can make consistent with different colors. And we just need 4 colors. Doesn't matter if it's these 4, but we need 4 colors. What you're going to do is 50 times you are going to pick one of those marbles or pieces of paper or whatever it is out of a bag, look at it, tally the results, and put it back in. 50 times you're going to do one at a time, taking this and doing an experiment. So let's say, I'm just going to make up some data here. Let's say that red we got 15 times. Make sure you're doing your tallies correctly. So tallies, we put those marks, and frequency, we actually put the number. Let's say blue happened 9 times. Green happened 12 times. And let's see what I have left. So 59, 24, so I have done 36 experiments, so I must have gotten 14 on my yellow. Once again, I'm just making up this data just to show what exactly you're going to do once you do your own experiments. So let's say this is the data that someone got for their experiment. It says, number 5, what is the experimental probability of drawing a red square, blue square, green square, yellow square, expressed each probability as a fraction and a percent? Well, let's say I were to just expand this table and say this is my experimental probability in fraction form. Well, I would have 15 out of 50 experiments, which I'm going to reduce a little by 5 and say 3/10. For my next one, blue, I have 9 out of 50. I don't believe that can be reduced any further, so that's my experimental probability. 12 out of 50 can reduce to 6 out of 25. And then lastly, 14 out of 50 can be reduced to 7 out of 25. So those are my experimental probabilities in my fraction form. And then in percents, I would say, and you can do this a lot of ways, you can get that denominator up to 100 or divide it and then multiply by 100. We get 30%, we get 18%, we get 24%, and we get 28%. So these are my percent probabilities for each of these different colors in my experiment. So which color are you most likely to draw? Well, here it's hard to know exactly which one is going to be the most likely all the time because this is just one experiment. But if I go based on the numbers, I would say red is the most common in my experiment, so that one is the most likely to draw. So experimental probability actually comes up a lot in real life, especially in sports. Baseball is a really good example of many, many different statistics that are truly just experimental probability. So in baseball, a player's batting average is the probability of the player getting a hit, actually hitting the ball and getting on base, based on his previous at-bats. It's typically expressed as a decimal to the thousandths place. For instance, if a player made 3 hits after coming to bat 10 times, that would be 0.3, but we would show it as 0.300 to that thousandths place. So that just came from doing 3 over 10. And so we're going to do the same type of thing for number 7. If a player gets 8 hits in 25 at-bats, what's the probability that he will get a hit on his next at-bat? So we take my experimental probability, 8/25, and turn it into a decimal. I would actually just get this to 100 and say that's 32 over 100, which is 0.32, and then there's a little 0 here at the end to get it to the thousandths place. Something like that would work just fine to find that experimental probability. In addition to sports, experimental probability is often used in banking, insurance, weather forecasting, business. So number 8 says a piston manufacturer is concerned with the likelihood of defects. And since this affects his costs and profits, it's a really important thing to know. The manufacturer inspects 250 pistons and finds that 8 have defects. So what's the probability of a piston that will have a defect? We want to show this as a percent. Well, what we are saying is the number of defects out of the total number that he looked at is 8 out of 250. Well, you can go ahead and just do 8 divided by 250, and you will see that this ends up coming out to be 0.032. But that's our decimal form. So I need to multiply this by 100. Visually, this looks like moving the decimal 2 places to the right, and we get 3.2%. B, if the same manufacturer produces 3,000 pistons, about how many will have defects? Well, what we are saying is based on our experiment, 3.2% of those 3,000 pistons will have defects, which actually means what I'm doing is taking this 0.032 and multiplying by that 3,000. So when we do this and take some time to actually figure that out, pause the video, multiply it out, comes out to be about 92 pistons is what we're looking at that in 3,000 would possibly have defects. Now see, we're going to look at a lot of different pieces to this. What it says is pistons sell for $35. It costs $25 in materials to make each piston. How much profit would the manufacturer likely make on 3,000 pistons if defective ones cannot be sold? So let's figure out some different amounts here. So if I were to actually sell all of those pistons, well, I would be able to say, oh, I make $10 profit from here to here because sell for $35, cost $25, so profit of $10. But I can't sell all of those pistons. I can actually sell 2,900 and 2,908 of them. It's also very tempting to just say, oh, if I can sell that many of them, then I multiply that by my $10 and find my amount. It's actually not what we're going to be able to do here, not what's going to happen. What I need to do is figure out how much does it cost to manufacture all 3,000 pistons, because we have to manufacture all of them. We have to make them to figure out if they have a defect. So what we're going to do is say those 3,000 pistons cost $25 each to make them. But I can only sell 2,908 of them at $35. So we're going to get this number, and that's where we would find the difference between them. Work that out for yourself here. Take a second to do that. And then come back and see if you get this final result. All right, so take some time, figure out, okay, if I actually sell them for $35, the ones that I can sell, minus how much it costs to make them, 3,000 times $25, work it out, make sure you get $26,640. Okay, so it is less than if we just said $10 profit for those 3,000 pistons. That's not going to work. And we can't even do $10 for those 2,908 pistons because I still have to manufacture all 3,000 of them. Hopefully you're seeing that connection there. All right, last little bit of this investigation is about random events. A random event is an event whose outcome cannot be predicted. For example, drawing a card labeled 8 from a bin of cards, each labeled with a number 1 to 100. This represents a random event. An experiment could be conducted to determine the experimental probability of drawing a card labeled 8. However, it's not always practical to conduct an experiment to determine the experimental probability. Okay, think about if you were to figure out if cereal boxes actually had those winning prizes in them in a ratio of 1 to 3. Well, you're not going to actually go to the store and buy 100 boxes. That would waste money, it would waste time, it would waste resources. So we simulate what this is going to be like. We simulate it with a random event using models such as number cubes, spinners, coins, random number generators. Okay, now 9 and 10 I'm going to leave for you to do here. I'll just kind of set them up with you, but use the information in Lab 1 in order to find those random numbers on your calculator. So this says Saxon O cereal is having a contest. Each box of cereal contains a prize piece and claims that 1 in 8 pieces is a winner. Conduct a simulation to determine the experimental probability of winning a prize piece within 50 boxes of cereal. To simulate this problem, use digits 1 through 8, with 1 representing a winning prize piece. Use your calculator to generate 50 random numbers. So what you're going to do on that number generator, I'm not going to show it in this video, you can go back to your lab to remember how to do this on a calculator, but you are going to say my range is from 1 to 8, and I want 50 numbers to come up. You can also do this in groups of 10. It might be easier to make sure that you're not missing a number or something like that, but every time a 1 comes up, that means that we have won. So what I would do is I would set up a little table, and I would say, all right, how many times did we get the number 1? How many times did we get the numbers 2 through 8? So I would maybe count it up or tally it up, whatever it might be, in those 50 experiments. And then I would then have, out of 50, how many times did I actually have a winner? So number 9 and 10 you can do then for yourself according to your simulation. What's the probability of winning a prize? So is it that 1 in 8, or did your experiment show something different? Number 10, how does your answer in problem 9 compare to the likelihood stated on the cereal box? So compare your answer with that theoretical probability that they give on the cereal boxes. All right, so with all of that and with the investigation practice, I hope that you are able to understand simple probabilities a little bit better, especially coming up with simulations or finding real life situations where probability happens. I hope this investigation, this video, helps with your homework and for studying.